See, last lecture we talked about the first part of Chapter 2 in the textbook. This is a basic theory about transduction. And now, as we will see, and I'll explain to you, reciprocity plays a big role here. So we're gonna go through that. Now, we've been through this before last quarter, right? And but we're going to go in more depth this quarter. We did a demonstration last quarter. Do you remember that? With that metal strip that's kind of looked funny. That demonstration is listed here down below, but there's no reason to do it again. You've all seen it. I'll just remind you of it when we hit it. Okay, well, so what is reciprocity? Well, you know fairly well what it is. And I'll remind you, but the amazing thing about reciprocity is that it occurs in just a huge variety of physical systems. And I don't think there's any, I don't see how there could be a general theory for reciprocity that covers all those systems. So what my impression is that I have seen it proved in certain situations, general situations, but not over all kinds of physics. And as we'll see, it's remarkable. It's not obvious, and as we will see, it's very useful. So here's the. Let me remind you of last quarter. Here is what I feel is the best statement of reciprocity. It's to, first of all, define what engineers call the transfer impedance. So remember, impedance has the form of drive divided by response. Now we're not specifying yet what this drive is. This is kind of nebulous right now, but that's really to be expected because this idea of reciprocity covers all kinds of physical systems. So for right now, just think of there's some kind of drive, some kind of response. We haven't uniquely specified it, but we will for our case. The transfer impedance is where you drive at one point and you look at the response at another point. It's the ratio. So it's like the impedance at one point, which is the drive at one point divided by the response at that point, but now it's transferred to some different spatial point. Okay? Now, so we're going to call Z12, define it this way. And now let's consider the so-called reciprocal case where we interchange the drive and the response. So now we're driving at point 2 and looking at the response at point 1. So the transfer impedance there will be Z21 because we're now driving at 2 and driving 1. And reciprocity is simply that the transfer impedance is symmetric. That Z12 equals Z21. That's it. Now, there's more to it than that because we haven't defined specifically you can't just choose anything for the drive and anything for the response. All right? You'll see that on the next quiz. I'm pretty sure that's on the next quiz. And it's pretty simple. So we haven't, but this is the idea. Okay? Now, the way we usually think about it is, this is fine, it's kind of mathematical. We can make one more step here. Imagine setting, this equal to the ratio when 2 and 1 are interchanged, okay? Which is just an explicit statement of this. If the drive is the same at the 2 points, then we can cancel the drive, right? And what do we conclude? We conclude that the response is the same. So that's the sort of physical, technically a special case of this, but it's a nice physical statement. That the same, if you interchange the drive and a receiver, okay, so the drive remains the same, the response has to remain the same. Now, as I mentioned, we haven't defined what the drive and response variables are. Yes, typos here. This can vary from system to system. okay? It only holds, reciprocity only holds for what you can call conjugate variables, specific quantities here. And it may be, I don't know this, but my suspicion is that if you're dealing with some physical system, you may be able to change the definition of the drive, but you'll also have to change the definition of the response, as long as you have these so-called conjugate variables, but I don't really know. Now, for what we care about, oscillatory mechanical systems, you know, like a driven mass on a spring, the drive is the force, and the response is the velocity. For electrical circuits, which we also, of course, have to care about, we care about these equally in transduction here, right? The drive is the voltage, and the response is the current. So that's all it's going to concern us. It's very simple for the variables. But there is this larger issue there for other physical systems. And in fact, we will encounter a physical system here, a mechanical system that's not an oscillatory system. And I'll talk a little bit about that. So why is it important here? Well, you really have to wait and see to fully appreciate this. But let me just tell you now that it's important for several reasons. It will relate the transduction coefficients here, as we'll see that today, I think. It will give us a relationship between the transduction coefficients. So that's really important because in our general theory, you know, these are independent quantities. Remember, this is the transduction going from the mechanical side to the electrical side of a transducer. This is how much coupling you have for a mechanical excitation, what electrical excitation you get out. And this is going the other way. So it's not surprising. It sounds a lot like reciprocity, right? These things should be related by reciprocity, and they are, as we will see. And here's another, a practical case. It leads to a connection between the receiving sensitivity of a transducer in relation to its transmitting response. So if you've got a reciprocal transducer, and you want to characterize, let's say, its reception, its sensitivity as a function of angle, you know, some kind of hydrophone, let's say, you can actually drive the hydrophone and look at its transmitting response, and then you get this, it's the same thing. Okay? So often one of those is easier to do than the other. Okay, so I can't remember what I said about this last quarter. I don't think we talked about this. Does this look familiar? This is an electrical circuit. It has to, sorry, I missed this. In the notes here, you'll see reciprocity only holds for linear systems. So if you double the drive, the response has to double, for example. If the system is not linear, forget it. Okay? Doesn't hold. So this is one of the, when I was a graduate student, this was one of the first systems. People seldom, let me back up here. People seldom talk about reciprocity. It's only in like advanced graduate studies that you get it, typically. And so I don't know. So I was a graduate student. I didn't know anything. I had heard a little bit about reciprocity or something, but I think we encountered this circuit in a class I was TAing. I was a teaching assistant for. But anyway, this is a really good example of reciprocity. So here's the idea. We have this. These can be any impedances here. They just have to be linear. So this says a diode's not linear, okay? So no diodes, no non-linear. They have to be any linear elements here. You know, the standard ones are capacitors, resistors, and inductors. It can be anything in these boxes right here. The electrical circuits like this, linear electrical circuits, obey reciprocity for the voltage and the current. So what that means is that if I look at the transfer impedance here, Z12, the ratio of the voltage to the current here. First of all, you can kind of see the need for linearity. If I double, well, remember reciprocity is this. And Z12, in our case, is going to be V1 over I2, right? This number, for a linear circuit, if you double the voltage, what's going to happen to this ratio? Double the voltage, you double the current, it's going to scale out. So already there's an indication right from there that you could be in trouble for a nonlinear system. You know, it's possible you could still get out of it, you could have some amplitude dependence, and you could still have this, but I don't know anything about that, but I think it's probably very difficult and probably not useful. That's my guess, but I don't know. Okay, so the idea here is to prove reciprocity for this system, to get a belief in it, get some feeling for it. Okay, so how do you do this? Well, we're going to leave most of this for for the next problem set, which is whatever according to the syllabus. I really don't know. Oh, it happens to be Wednesday this week, right? Okay, it floats, right? But here's briefly the idea. This voltage source here sees an equivalent impedance here, right? And the equivalent impedance, I see this impedance in series with this two impedance. So this thing sees an impedance, which is the impedance A, plus the parallel combination of this. And you know the 1 over the impedance, the equivalent impedance across these two points right here, 1 over that's going to be 1 over B plus 1 over C, right? Impedances in parallel, add in reciprocal. So we know that this is what the impedance, and here I've written, converted the reciprocal, 1 over the reciprocal, converted it here. We'll go through all this. So this is the impedance seen by the source here. For this diagram right here. Once we know, this is the standard way of doing it, once we know the impedance here, we can find the current right here. The current going through here, the current here, which is the same as the current here. Once we know the current here, we can get the voltage drop across here. Once we know the voltage drop across here, we know the voltage drop across here, so we can get the currents, which means we've got that current and we can find the ratio. We can find this. Now, if that sounds like work to you, it is. And we're going to do that in the problem set. Okay? And here's the result that you get when you do that. The result is that the transfer impedance is this in terms of the impedances. All right? So we'll derive that. It takes a fair amount of algebra. Now, let's look at the reciprocal situation. Let's move the voltage source over here. Move the current meter, over here, right? Do we have to solve the whole system again? Do we have to go through that whole process? No, because the reciprocal situation here is identical to this situation if you interchange A and B. Just look at it. If I interchange A and B here, I'm going to get this. So we can find Z21 simply by taking this result and interchanging A and B. And what happens? It's the same. So we just proved reciprocity for this system. Now, I want to point something that's important for you to realize something here. And I might have briefly mentioned this last quarter, but I don't think we got into it. Let's go to our original circuit here. What if A equals B? Is the transfer impedance going to be reciprocal? Does reciprocity hold? Obviously, because it's symmetrical. If A equals B and I interchange the source and the receiver, I'm not changing the system. So it has to be reciprocal. But there's something, here's another case. Suppose C were infinite. Suppose we essentially yank this out of the circuit. it's obvious that the transfer impedance has to be reciprocal, because this circuit is then going to be the same as this circuit. It doesn't matter the order that you see here. But when you put this in here, it's not obvious, okay? So, and this is, I think, always going to be the case with reciprocity. There are special cases, special geometrically symmetric cases where it's obvious that reciprocity has to hold, but it holds in general. It holds no matter what A and B and C are here. And that's not, it's just not obvious. It's a kind of, I call it a hidden symmetry. Because it's not obvious. Okay, so here's the next example we're going to look at. This is similar to the demo we did, but it's simpler. You have a rod that can flex here. It's clamped here. Like this, like what you see right here. Okay, I'm clamping it here. This is rigidly clamped. And we're going to look at static equilibrium. So this is outside what's concerning us. You know, we want oscillatory mechanical systems, acoustic mechanical systems, and oscillatory electrical systems. So this is a static mechanical problem here. So all of a sudden you need to know, well, what are the variables? Well, it's just what you would think. And you know, these variables probably aren't unique, but the standard conjugate variables here is the weight here. I'm sorry, we're going to suspend a weight at one point and look at the displacement at another point. Okay? And those are the variables. Those are conjugate variables. So reciprocity tells us that if we suspend the weight at one point, that's our drive, and we look at the response, which is the displacement from equilibrium at any other point, that the ratio of those two things, well, so, sorry, let me say it again. We suspend the weight at one point, right? Look at the displacement at another point. We measure a certain displacement here. If we then take this weight and apply it at that point and measure the displacement here, what do we get? The same as the displacement here. It's the same. Now, it's clear when you move this over here, you're exerting less torque, right? Oh, why isn't torque the right variable to use here? Anybody know? I don't know. But it doesn't work. And that's the subject. Oh, maybe I'm saying too much, but there's something on this on the quiz. I don't think I should say any more about it. But it could be that torque could be used here, okay? But what I want to tell you right now is that these are conjugate variables. If you use this as the weight and use this as a displacement, those are conjugate variables. And you may wonder if there are other conjugate variables, but that's on the quiz. So I don't want to say any more about that. All right, so I apply the weight here, I get a displacement. It'll be something, right? And we did this for that bar that was weirdly shaped, the aluminum strip. And I didn't make that. I don't know if I told you guys the history of that. The professor who previously taught this course for many years here, in basically the 2000s, he was a big expert on transduction. He made that, and he used it when he taught the course. And I think he picked it up from an acoustician, somebody who does acoustics, among other things, at Los Alamos National Lab, a guy named Greg Swift, who's famous for thermoacoustic refrigeration. You can use acoustics to refrigerate. Did you guys know that? Yeah. So, but that's another course. So anyway, I think, I never asked him and he never told me, but I think it was all contorted like that to kind of show how general reciprocity is. It doesn't have to be this nice simple case right here. Okay? I think that's why that was done. So anyway, we move the weight over here. Reciprocity tells us the displacement here is going to be like here. It's going to be the same there. Now, qualitatively, it is obvious that if I move the weight from here over to here, what's going to happen? There's less torque, so the rod is going to bend less. right? It's obvious. And in fact, you can reduce this to an absurdity. If you take the point of application here and keep moving it over, all the way over here, what happens? No displacement. Now we're neglecting sag here. Don't worry about it. This thing has some mass. It will sag, but let's assume it's sufficiently stiff that the sag, for convenience, don't worry about the sag. Reciprocity will still hold if you have the sag in here. Okay? If this thing is in equilibrium, is sagging like this, and you put a weight on it and it goes down even more, you'll still, as long as you measure from equilibrium, and it's linear, and everything's linear, reciprocity will still hold. So it is clear qualitatively that when we move this over here, that the bar will sag less. But it's not at all obvious that the deflection here is going to be the same as the deflection in our original case. That's not obvious. And that's reciprocity. Okay, let me make sure I've covered all this. Yeah, okay. So I put this in here, but every year for the past several years at least, there's no reason for us to do the experiment, right? The demonstration. We did it, and it worked pretty well. And I've never pursued this quantitatively, but my suspicion is that the deviation that we saw last quarter, I think we wrote it out right here on this, I think it was right here. Can't see it anymore. Maybe you remember though, there was some error. It wasn't exactly the same displacement. And I think I might have told you that it could be due to nonlinearity, because we're looking at pretty good deflections here. And this linearity will break down. This is not, deflection of you would suspect that when you deflect something like this statically, it's not linear, and it's not. It's well known, it's a standard topic in the theory of elasticity, what the displacement is for a given force here at some point. And it's not simple. And it's not linear in general. I wanted to ask a question here. This is on the lines of the contorted strip, okay? To do a demonstration, and actually someday I think I may switch to this as the demonstration, okay? Rather than the contorted thing. If you wanted to do that, the natural way to set it up is you have an upright here. You have your rod here, right? You're going to apply a weight, and then you put a crossbar with another upright here, because once you apply this weight, there's going to be a tendency, of course, of this upright to flex too, right? That would be an obvious thing to do. Now the question I want to ask you is, suppose we don't have this. And this is not very stiff compared to the rod. An alternative is to make this very stiff compared to the rod. But my experience is, even when this is a typical upright, 3/4 inch diameter, and this is like, this could be much less, you're going to see this thing flex. I just know this from a huge amount of experience, okay? So even if this is, looks substantially bigger, stiffer to you, I think you're going to see it flex. So the question is, does reciprocity still hold?
As long as it's in the linear.
That's true. See? And you think, Dan's absolutely right. It's a very general thing. Once we remove this other upright here and this crossbar, and we take into account that this can bend, now we have a more complicated system. It's actually, maybe that's why they did this thing, right? Maybe that was their way of, Swift's way of indicating that. My feeling right now is, it might be interesting to do the demonstration this way and then remove these and redo the demonstration where you can clearly see this flex. So when you apply the weight, you're going to get a greater displacement without this, right? But when you do the reciprocal situation, when you move the weight over here, it's also going to be greater, and they should cancel out. Reciprocity should still hold, as long as everything's linear. So you might think, and I've gotten ahead of myself here, you might think a torque would be the natural variable here. Take the weight times this distance. That seems like a natural derived variable. So the question becomes, okay, what's our response variable going to be? Okay, that's a natural question. And so that's the subject of the problem in the quiz. So I don't want to say any more about it. And it's simple. So here's another one. I distinctly remember this when I was a TA. This is another one that hit me. So this was bothering me back when I was a graduate student, this reciprocity. And so here I am, you know, freshman, and probably talking about reciprocity. I probably should not have been doing that, but I just couldn't stop myself because it's amazing. I didn't spend a lot of time on it, but I distinctly remember doing this problem. You can solve, this is another static equilibrium problem, okay? You have a string here under tension. You can see it, you apply a weight at some point here. Now, you need to be careful here. We can only have small displacements because this is in general a nonlinear system. Doubling the weight won't double the deflection here when you get to big deflections. My guess is because the tension is going to go up. When you pull this thing down here, the tension goes up. Does this sound like waves related to waves on a string? That was a topic in 3119, right? Now, for linear waves on a string, do you remember what you assumed about the tension in the string? For small amplitude, it's the same, right? You have to go to higher amplitude for it to see a significant difference in the tension. That makes, you know, assuming constant tension, that's the only way you get the wave equation. You don't assume that, it's a lot more complicated. It becomes a nonlinear system. So we can do the same thing here, as long as the displacement is not, this is probably too much is what I've shown here, okay? But we only want to look at small displacements. Because the tension is, for a linear system, is going to be constant here, just like it is when you saw the derivation of waves on a string. Reciprocity should hold. So if I look, and again it's going to be the weight and the displacement, those are the conjugate variables. If I put a weight here and look at the response at some other point, I measure this. If I then move this over to this point and look at the response here, it will be the same. Now in this case, we can qualitatively see why reciprocity, similar to a previous case. For this particular situation right here, when I move this over here, how much sag do I get here? How much is this point going to go down compared to this case? See, this point is closer to the center. Where do we get the maximum deflection? Where do we put the weight? In the middle, right? We get no deflection if you put the weight at the ends. All right? So we're going to get a greater displacement here than we get there. But on the other hand, this point is closer to this node here than our original point is. So there's competing effects there. Reciprocity tells us those effects exactly cancel. So when you move the weight over here, this distance right here, which the reciprocity tells us will be the displacement there when you move the weight over. When you move this over here, you're going to get a bigger you're going to get a tendency for this to be bigger. But the fact that this is closer to there than this point is, this point is farther away, that's going to tend to reduce the displacement. They exactly cancel each other. Not obvious. So I remember going through this. This is not real simple, but for the linear system, you can solve it, and you can probably see that this is, you know, these are going to be straight lines, right? We're not worried about them. We're neglecting the mass of the string, so we don't have, you know, this sagging here, similar to the bar. So with some effort, you can solve this. Takes a little bit, takes some algebra, and you can prove reciprocity in this case. Now again, I want to remind you, if we take our driving point, let's say our driving point's here, if we then choose our measurement, our deflection point, to be the diametrically opposed point over here, okay, so that this distance equals this distance, if I interchange the drive and the response, it's obviously going to be the same by symmetry. But reciprocity holds for any case. Shows you that it's true for any case. Okay. Anybody have any questions? So that's sort of background on reciprocity. And you can see we went into it more deeply here. I don't know what I can't remember. I just remember we did the demo last quarter. I defined transfer impedance and we did the demo. I can't remember what else we did, but there's I think it's more important in this course, much more important. So that's why I wanted to give you some more examples here. So let's now, what does this have to do with transduction? Well, first thing to note is that reciprocity holds, as I mentioned to you before, any electrical circuit that has linear elements, reciprocity is known to hold. Okay, where the conjugate variables are the voltage is the drive, and the current is the response. So what that means is, however, we have to clarify this a little bit here. That's the purpose of this diagram from the book here. So let's consider this arbitrary linear electrical network. It's arbitrary. And there can be any number of ports, okay, terminals. Any number, and it's arbitrary. Here, this N stands for network, I guess. So you pick two of the terminals and you put a voltage across there. And oh, I'm sorry, I didn't even think about this. You can think of the voltage as DC or AC, doesn't matter. I think I even mentioned that. Yeah, it's pretty obvious, but I should mention it. So you have these two terminals. You pick any other two terminals. And the idea there is that you want to look at the current, okay? Now, this is, I don't know what to call this, clarification, specification or something. You need to to look at the terminal, to look at the current, you've got to short out. That's the only reasonable thing to do, is to short it out. If you don't do that, if you have a current meter here, you're not going to get any current, okay? So the meaning here is you actually have to create this other, you're creating a loop here. You know, we don't have any problem with putting a voltage across 2 points in a circuit. Okay, but if you want to measure the current between those 2 points, you need to specify something. Here's what it is. You're going to put your current meter in here and short it out. That's what we mean. It's not as obvious as what's going on there. So that's what we mean. So the fact that reciprocity holds means this. Mathematically, this J and K refer to a pair of terminals. Okay, the jth pair, this is the kth pair of terminals. We put a voltage across the jth pair. We look at the current across the kth pair in the way that I just described to you. That's the transfer impedance. To specify that we're shorting out those 2 points, we really have to do that to measure the current. We put VK is equal to 0. Shorted, okay? So the transfer impedance being symmetric, that is to say reciprocity holds, means that the transfer impedance from J to K is the transfer impedance from K to J, going the other way. So the voltage across K divided by the current across I, when you short out I, those two things will be the same. So that's a mathematical statement of reciprocity. Don't worry, this needs to be modified. This was something that bothered me in the past, and now I realize it was just not relevant. Don't worry about this. It's going to be modified, edited. Okay, so it's pretty simple, right? But it may look complicated. I have to hang on this mathematical stuff here. But we need to do that to be precise. Well, this looks a lot like the model for our 2-port general two-port electroacoustic or electromagnetic acoustic transducer, right? So the transfer impedance being symmetrical here, what's that going to mean? It's going to mean that, and now we lose the indices, which is nice. It means that, thinking of this as the drive, okay, the voltage divided by this, carrying over this current here, which is now a velocity, mechanically it corresponds to a velocity. We're in the impedance analogy here. It means that the voltage divided by the current, when this is shorted, which now means free, no force, so there's the no force, that has to equal the reciprocal case where we look at the drive being the force now, divided by the electrical current when you short that out, when the voltage between the terminals is 0. Now, another homework problem we're going to do, and I just naturally put these into the homework because this is, I've told you guys this before, this is a complicated course, okay? And really nothing seems to be real simple here. So it looks like this might be simple here, but it actually takes some, Brian doesn't do it. And so I remember I sat down to do it and it's surprising. The derivation, it has a kind of wrinkle to it. You'll see, we'll do it in the problem session. But here's the idea. We take the canonical equations. Remember, way back here, it's probably on page 1. Or maybe not. Yeah, there they are. For a linear transducer, a double two-port, you know, like this linear transducer. We take these equations and we demand that reciprocity hold. Okay? If you demand that reciprocity holds, we're going to show in the problem set on Wednesday, discussion on Wednesday, we're going to show with some effort that it only holds if the transduction coefficients are the same, symmetric. If the reciprocity symmetry also holds for the transduction coefficients, which is actually quite reasonable, right? Because this is, as I said, this is the coupling from, you know, going from one form of energy to another. So you can kind of see a transfer impedance there. So it's not, I don't think it's real surprising. What's surprising is that the math is not trivial. Let me just put it that way, as we will see. So this works both ways. This is an equivalence. Our canonical system, transducer, is reciprocal. In other words, it obeys reciprocity if and only if this holds true. Okay, they're equivalent. What concerns us is going this way. If a transducer is reciprocal, the transduction coefficients are symmetric. The reason that's important is that we will be able to, and I'm actually saying this without proof, and I didn't find a proof anywhere. I remember struggling a little bit with this. But it's reasonable that if we have this, if we have a reciprocal transducer, there's going to be an equivalent electrical circuit. All electrical circuits are reciprocal. So you know, here's another logical way of looking at it. If we have a transducer that doesn't obey this, are we going to have an electrical circuit? No, we can't. All proper, you know, linear electrical circuits are reciprocal. If our transducer is not reciprocal, we don't have an electrical circuit, and that just blows transducer people away. They do not accept that. because they have to use electrical circuits. And you'll see why after you get been through this course. It's just the only way to do them. So we're going to find that not all of our transducers are reciprocal, but there's a way around that. Okay. Fortunately, almost all of the transducers we're going to consider will be reciprocal. And looking ahead a little bit, I'll tell you right now that the ones that aren't reciprocal, that don't obey this, are anti-reciprocal. What do you think that means? Take a wild guess. Don't think too much about it. Yeah, there's a negative sign in here. That's exactly right. Okay? We will be able to handle that. The only way we're going to be able to handle that is if we switch the analogy, as we'll see. We go to the mobility analogy. Remember? The King Kong. Did I tell you guys about King Kong? Oh, sorry. The mobility... The mobility analogy came out the same year that the original King Kong movie came out. Now, I don't know if that helps you in the timeline there or not, but it helps me, because I'm interested in old movies, but classic movies. So I don't know if that helps you. But anyway, so 1933 is when somebody finally published that. And I don't know if it was around before or not. But that's what's going to save us when we deal with an anti-reciprocal case. So we're going to do that this chapter. That's coming up. Okay, so any questions? So that's what the basics of what we need for reciprocity. So now what we're going to do, following the book, is we're going to do an example. And this is not simple. It's going to take pages to do this, okay? And I didn't like the way Brian did it. I looked at some other books. I kind of found my own way that I thought was good to do this. So we're going to go through all this. And then naturally, when you're going through something, you think, well, there's got to be a simpler example, right? Well, I couldn't find one. So what we're going to begin it today, just get just some basic introduction to the problem. It's really the simplest case, and it's not simple at all. And it will also lead to a possible demonstration that that Faisal might be doing for his thesis. I'll talk about that when we get to it. That's going to be a few lectures away. Okay. Probably tomorrow. I'll talk just a little bit about it. So let me remind you what we mean when we talk about an electrostatic transducer. That has a specific meaning for transducer people. It's where you have a capacitor and one of the plates moves. Both of them can move, but typically we're just going to consider one that can move. And this is a reversible transducer, okay, in our previous language, because you've got this capacitor here. We're going to just take this plate to move rigidly. Did you think that's what happens in practice? Very seldom. What happens in practice? It's going to flex, right? This is going to be anchored down here, okay? But for simplicity, we're going to take this effective, just treat it like that. If we charge this capacitor up, okay, with some voltage, and then on top of that we put an oscillatory voltage, what's going to happen? Well, when I increase, let's say this is positive and this is negative, when I increase the positive charge and increase the number of negative charges here, the attractive force is great. It's going to suck this thing in, okay? And going the other way, it's going to go like that. So if you do this at some frequency, you're going to send out sound. That's the whole idea behind an electrostatic loudspeaker. Achieving that, though, takes, and I was just moving that thing around over the weekend. It's really, I should have had all you guys try to lift this thing. It's very heavy because it takes kilovolts here. There's big transformers in there. That's a practical issue, though. From a fundamental point of view, this can be a driver, and as you know, it can be the receiver, a microphone. And I don't know if I mentioned it last time. I don't think I did when we talked about this. This is now the most common microphone. Condenser-type microphones are the most common. Oh, wait a minute. No, I think they've been beaten out by Electret microphones because they're cheaper and more durable. Yeah, I take that back. But but those don't work real well for measurement purposes. The standard high-quality measurement microphones are this. So now a sound wave's coming in, right? So in this case, we're not going to drive it, right? We do need to keep the charge on there. That's a problem. I'm going to talk about that in a minute. So we assume we have this charge capacitor. A sound wave comes, causes this thing to flex, okay? And if the charge stays the same, what happens to the voltage between here? The voltage, remember the voltage, we'll see this so many, I told you guys so many times in this course. For a parallel plate to capacitor, where the plates are, where it's a uniform field between, so the plates are close, the voltage is the electric field times the distance. And when we start using this more, I'll tell you physically what's behind this, because we're going to use this so many times. I don't want to take the time right now to do it. But the point here is that if the charge stays the same, the electric field is the same, but our distance is changing, so therefore the voltage will change. So it's a transducer. It's called a condenser or microphone. Now, this is from the textbook, and I naturally looked into this because, from a practical point of view, how do you keep the charge on here constant? Humidity will discharge it. Well, you got to have a DC, as we mentioned, you got to have a DC source here. But there's a problem. Here's my variable capacitor. Okay, think of this as a microphone here. So the sound wave is going to change the capacitance, right? And if we just put a DC voltage on here to keep this charge, forget this for the moment, just short that out. What voltage are we going to measure? The sound wave comes by, it causes this. What happens when this happens? What happens when it gets closer or farther apart? Well, the job of this thing is to keep the voltage across here constant. So what are we going to measure? No voltage change. What's going to happen is, when the plates get closer together, electrical charge is going to flow to increase this in order to keep V constant, because that's the job of this. So that's not going to work. So how do we handle this? Well, this is a practical issue. It's very simple. We put a resistor in here. I think this is a little confusing, this B. I'm going to call this capital A. I'm going to edit this. But this is we put a resistor in here. What does that do now? Now there's a time constant. The characteristic time it takes to charge, suppose this is uncharged and you've slapped this on here, you connect this. The characteristic time, it's a 1 over E thing, to charge this up is the time constant, which is the product of the resistance times the capacitance. You might remember that from electromagnetism. So what they do here is you choose the time constant to be long compared to the typical period of the sound wave. The sound wave's coming here and it's modulating this distance, right? If the period there is much less than the time constant, this voltage here will not be able to change the charge on there. It's happening too fast. So that's a practical consideration. And where is it? Oh, here it is. So the time constant is much greater than the period. It just doesn't have the time to change the charge on there. But over a long time, due to the discharging, it'll keep the charge there, right? Perfect. It's obvious, but it's just something it's important to see. This is typical for transducers. There are these practical considerations you always need to think of. Okay, now there's one other problem. This is not so obvious. In fact, to be honest with you, I never thought of this one, but I found it in some book. It's not in Brian's book. We've got, for an electrostatic loudspeaker, this V0 is huge. It's many kilovolts. So you might worry, here's your transducer. Here you have, in general, there's some electronics here. If you've got this high voltage here, you could be putting current. You could destroy some electronics here. So you want to put up what's called a blocking capacitor, what they call a blocking capacitor here, that will cut down won't allow for any current to flow in there. Now, what do you choose this to be? Well, this is a little bit more nebulous, but there's going to be a, when we have our signal here, we want this to act as a short. We don't want this to change the signal we're getting out, you know, from our sound. I'm now thinking of this as a microphone, okay? Look at it from that point of view. We're changing this at some typical frequency. It would be a nuisance and maybe even worse, I don't know, if we had to deal with this. So we can easily take care of that. We want this impedance to be much less than the typical, whatever impedance you have here. So I put that in terms of the load resistance. I guess this is just roughly right. There's some typical resistance here. You want this impedance to be small compared to that at the frequency that you're detecting the wave. Then this will act as a short. But it will, because this is a DC, it's going to block, you know, at zero frequency, this is zero frequency, it's going to block any harmful current that can come in. Okay, so those are two practical considerations that I thought would be good, that aren't in the book, that I thought would be good to tell you. We will now neglect those. Okay, we're going to have our hands full. We're going to deal with Brian's circuit here, okay, which doesn't have these things in there. We're going to find that this is sufficiently complicated for us to deal with. But you want to realize that if you actually want to make this, you're going to have to add these things. Now let's see. Okay, quickly, one more thing here. This threw me when I first saw this. When we go through the theory here, is this going to be a receiver or a transmitter? When you look at the canonical equations, are they for reception? Are they for a receiving transducer or a transmitting transducer? Well, they're both. We're not specifying it, which is actually convenient. We can go through the theory, and then later on we can apply it. If we have in mind a transmitter or a receiver, we can go ahead and apply it to that. So, and that just caused me trouble when I first, because I didn't know anything about this stuff. So we're really thinking of both cases here when we do this. We're really, when we go through the theory, we're going to be able to apply that theory to both, and that's very convenient. We don't have to redo the theory. So, okay, so we will do that. We will go through this tomorrow, and then we'll get into the anti-reciprocal, where there's a minus sign between the transduction coefficients. We'll get into that tomorrow. Okay.